All right, so this one we're going to just start with an example. I might do two in this video and then do two more. You'll see after a while that they're all sort of more or less the same once you get the hang of them. So here's the state of stress, right, on the left. I've got minus 10 KSI for sigma XX, minus 40 KSI for sigma YY, and a positive 20 KSI for tau XY. There's no reason that sigma XX has to be, larger or smaller than sigma YY or larger or smaller than tau XY, right? So they're all independent, right? But this is the state of stress in a XY orientation, right? Which we're just going to always treat as sort of horizontal vertical. Okay, so let's draw the Mohr circle. So I'll come out here, I'm going to draw it like this, and I'm going to draw it like this. Okay, so this is my positive sigma axis, and this is my positive tau axis, right? Okay, so first step is we're going to plot these two guys, right? So minus 10 KSI and a positive 20 KSI. Right? So I'm going to come in here, minus 10 KSI and a positive 20 KSI, and it's going to put me right there. Okay. And so this guy is a minus 10 comma 20. Like that, I'll do it here, minus 10 comma 20, right? And then the other one here will be minus 40. So 1, 2, 3, 4, and then a minus 20, right? Again, that is sigma YY, which is minus 40, and then minus tau XY. Right? So this guy will be minus 40, minus 20. Right? And again, it's above the axis, right? And it's above the axis because we're plotting tau positive downward, right? Okay, so now let me draw this red line like that. In fact, you know what? Let me do it in blue because that orientation up there is in blue, right? So that blue line corresponds to the stress that I'm showing in the upper left, right? And then I'm going to draw this Mohr's circle, right? And it's going to do something like this. I'm doing a terrible job. Yeah, let me try that again. Okay, close enough, right? So that's our Mohr's circle, right? And then we can say that the principal axes are right here, right? They are always horizontal. That makes this point sigma 2, which is the minimum, in an absolute sense. So this is negative, right? So that's a minimum. And this guy here is sigma 1. That's the positive. That's the maximum positive that we can have, right? And that this point here in the middle, right? In fact, I'll do it in black because it's not really associated with any particular stress state, is just minus 25 comma 0. Right? Okay, so let me calculate R, right? So this is R, right? That is the radius, right? So it doesn't matter which side I use, right? But it is effectively, I guess, let me do it in, what do I want to do this in? I guess I'll do it in green. So it is this dimension and that dimension, right? Those are the ones that we care about, right? Because I can square them and take the square root, it's going to give me R, right? So this vertical dimension is 20, right? And this horizontal dimension is 15. Right? So I started at 25, and then I went to 40. Right? So I moved 15. Doesn't matter positive or negative, we're squaring it. And then here I started at 0, and then I moved to 20, right, or minus 20. Again, doesn't matter, positive or negative, because we're squaring it. All right, so let's then go ahead and calculate these guys. So r is just going to equal the square root of 15 squared plus 20 squared, and that actually equals 25. Nice round number, right? So sigma 1 is just the center plus r, so that's sigma average plus r, right, which is going to be 0. Should add some units onto these guys. Sigma 2 will be sigma average minus r, so that's minus 25 minus 25, so that is going to be a minus 50 KSI, right? And then if I want to know my theta p, right, that's this guy, so this is what we're going to call 2 theta p, right? And so 2 theta p equals the inverse tangent of opposite over adjacent, which in this case will be 20 over 15, right? And that is going to give me a theta p of 26.5 degrees, and it's going to be in that direction, right? So on the circle, I'm rotating it counterclockwise, okay? So on the cube, I'm also going to rotate it counterclockwise, right? Okay, so let's now draw the principal state of stress, right? So I'm going to do my best to sort of approximate what 26.5 degrees looks like, but it should look something about like that, right? And we're going to have sigma 1, right? That's going to be in that direction. And sigma 2 is going to be in this direction. And we know that sigma 2 equals minus 50 KSI. And we know that sigma 1 equals 0 KSI. Right? And we do not have any shear stress because it is a state of principal stress, right? And we also know that the angle that we've rotated it, right, is 26.5 degrees. Okay. That, by the way, is also equal to this angle, right? If this is a square and I rotated it, every side rotates that amount, right? So how do you think about this in terms of the orientation? Well, we started, so this point here, right? So this point here, so this point here, and it's supposed to be on the circle, I understand it's a little bit off, but that point there is the X face, right? That is associated with those stresses. So that's the X face. So if I rotate the X face 26.5 degrees, right, and that puts it right there at sigma 1, then I should plot sigma 1 on that face. Right? And notice what happened. When I've rotated the X face there, the Y face rotates down to the horizontal plane. So I'm going to plot sigma 2 on the Y face, and that's what I did, right? Just like that, okay? So that's the X face. This guy here is the original Y face, right? So you're always rotating from that face. That'll tell you which one to plot, you know, sigma 1 and sigma 2 on.